now past 12 o'clock. So good afternoon, everyone. Welcome to our first DAFNI webinar for 2025. And thank you everyone for joining today. My name is Alison Oliver, and I joined DAFNI 5 months ago as the Research Community Manager. I will be looking after our website and assisting my colleagues in event management and communications and our partnerships. So we are recording this webinar, and there will be a Q&A at the end, and please could I ask that you send any questions to the questions box throughout the talk, and I'll go through those at the end. So I'm delighted to welcome Dr. Xilin Xia from the University of Birmingham today, who will present on the DAFNI-funded STORMS project, which stands for Strategies and Tools for Resilience of Buried Infrastructure to Meteorological Shocks. STORMS has developed a weather-related risk assessment framework to increase resilience to weather-related risks, including analysing soil structure and damage calculations for buried pipes, and DAFNI is being used for the workflows and visualisations. So I will now hand over to Dr. Xia to begin.
Yeah, so I'm just sharing my screen now. Yeah, hopefully everybody is able to see that now. Yeah, thanks. Thanks everyone for joining the webinar today. So this project, as Alison has introduced, is a project funded by DAFNI, by STFC, as part of the Building in Resilient and Secure World Center of Excellence program. So this project is led by the University of Birmingham and also involve the two research organizations, the UK Centre for Ecology and Hydrology, and also the British Geological Survey. I think we have a relatively large and interdisciplinary team covering different aspects of the project. So I will start with some introduction. Why we want to look into buried infrastructure, because we don't usually see it in our day-to-day lives, but in our underground space, there are a lot of things there. There are a lot of pipes running across our along and across our streets and lines. This picture just illustrates how complicated our underground space actually could be, and they are very essential for our daily lives because they provide essential services such as water. There are a lot of water pipes down there, and also energy. There are a lot of natural gas pipes there, and also electricity cables running through the streets. And also very importantly, a lot of telecommunication pipes, such as the fiber networks that run through to connect us, such as telephone and internet. So they are really essential services. So this is really a critical part of our infrastructure. To give you some better ideas, these are some numbers from various governments and company reports. For example, in England, Wales, we have over 350,000 kilometers of water mains and over 500,000 public sewers. And in terms of gas distribution pipes, we have over about 280,000 kilometers of gas distribution pipe, and also a similar number for electricity network that is buried underneath. There's altogether there's over 800,000 kilometers. And in terms of the damages to those pipelines each year, there is over 2.4 billion pounds per year of damage being caused to those pipelines. So it's so just by summarizing these numbers, I think there's a lot of buried pipelines that are supporting our services, and they are of very high economic value and now society pretty much relied on them. And unfortunately, climate change and the weather are actually having great impacts on those infrastructure, but maybe not as visible as some other things such as transport, but they do exist and they are significant. So before I talk about the actual impacts, I want to give a very high-level summary of how the climate is changing for the UK. So this is based on the last National Climate Risk Projection, UKCP 18. In summary, we are going to get warmer, wetter winters and hotter, drier summers. And this also means that we will have increase in precipitation intensity on wet days in the winter and possibly more drought in the summer as well. So the left at the right hand side are two figures here showing how the precipitation is changing during summer seasons and winter seasons according to the Met Office report, as we can see that that's a clear trend over there. And also, it means more pronounced variability of soil moisture, according to a paper published in 2023. So in this figure, the blue line is the current soil moisture average for each month in current day, and the yellow line shows how it might be it might look like in the future, as we can see that during summer months there is a drop in terms of the monthly mean soil moisture. So later we will discuss how this combined effect of both precipitation and soil moisture are actually having an impact on our buried infrastructure. So in terms of the impact from climate change on buried infrastructure, we have talked about how the climate is changing, but how exactly this could translate into impact. Generally, there are two different mechanisms that are the most significant. The first one is extreme flood events. This could cause the soil of the ground being washed off, and the buried pipelines are then exposed, which means that the structural integrity of the pipelines could actually be influenced and potentially be damaged as well. And there are other effects such as sinkholes and uproot of trees due to flooding, and also loss of load bearing of the soil as well, because wetter soil tends to be softer when heavy vehicles running on top of it. It causes the damages to the pipelines being buried underneath. Apart from the impact of a flood, which is possibly more visible, and there's also a long-term impact from weather and climate. This is mainly due to wet dry cycle and freeze thaw cycle. In the UK, maybe the wet dry cycle is a more significant problem. The basic idea is that when the soil goes through those cycles, it introduces some variability of soil moisture, which means that the ground would move differentially. Some parts may shrink a little bit more than the neighboring part of the land, which means that this differential movement can cause the breakage of pipes, especially for those pipes made of material that is more rigid. For example, water pipes made of concrete, or natural gas pipes made of cast iron. And so there's still a lot of pipes being made in this material. So they are particularly vulnerable to this kind of impact. So I've talked about the mechanisms of how those climate change effects and whether effects is having an impact on the pipelines. But in terms of the current status of climate risk assessment, there's still a lot of things that are unknown today. The climate drivers and the impacts are well known. The organizations, mainly the utility companies, they know their problems. So this has been highlighted in the last round of climate change risk assessment report, and also recent rounds of adaptation in reports from those utility companies. Just by looking at what the reports are suggesting, although a very detailed number hasn't been given, I think from an a reasonable estimation that there could be hundreds of millions of damages per year caused by weather and climate. But when we were having conversations with people from those organizations, such as the water companies, the natural gas companies, when they were coming up with the risk level for their assets, actually, in most of the cases, in those risk assessments are qualitative, they're very high level, and maybe just to give a very high level rating of risk for the entire network without any further granularity. And it's mostly based on expert judgment rather than some quantitative analysis of the data being there. So in a very short summary, a lot of research has been done about the climate and the climate drivers for the impact and the mechanism for the impact are well known. It's a well-known problem, but we don't have a lot of details and granularity on those problems. And therefore, a national scale quantitative risk assessment method is very urgently needed for the water, energy, and telecommunication sectors. So this is because if we have this, we can guide investment into climate adaptation, and especially given there's a lot of uncertainty on future climate scenarios and also the net zero transition. For example, some of the natural gas pipelines will be used for other purposes, for example, transporting hydrogen. This could change the availability as well. So given all these uncertainties and the intensifying impact of climate change, I think it's quite urgent that we have this understanding of where the risks are and where the hotspot is, how it's changing over the time. But we don't have a lot of knowledge at this moment. So this gives us the motivation to develop a comprehensive risk assessment model to guide decision-making for climate resilience. But to develop such a model face a lot of technical and non-technical challenges as well. So over the last 1.5 years, our team has been working really hard on addressing these challenges. The first one is that we need a new modeling techniques that is both rigorous and scalable. I've given you numbers of the total length of the pipelines. There are hundreds of thousands, in total, maybe millions of kilometers of pipelines. So it's really a large-scale problem, but we want to get a relatively quick answer. We don't want the model to run a couple of months. And we also need to have integrated a lot of data sets from climate, from hydrology, from geology, and also the infrastructure itself. And because we're dealing with some critical infrastructure such as energy and telecommunication, and water. And for some of them, the data set, it can be quite sensitive to handle as well. So the utility companies are not always willing to share the data to others due to some very legitimate reasons. So we have to come up with ways to overcome those barriers. And during the course of the project, we did gain some better understanding of how to do this. And in a lot of cases, the data are just not existent. So we have to make informed assumptions to make sure that we come up with practical solutions. So these are the some of the challenges that we have faced during the project. So I will now give you a bit more detail about the work that we have done. So this is a high-level summary of the climate risk assessment model we have developed. Basically, we're looking into two categories of risk relevant with the two different mechanisms I've just mentioned. The first one is the risk from surface water, mainly flood-driven erosion and accumulation as well. The other one is the risk from ground movement, either due to loss of load bearing or the differential subsidence or expansion of the ground. So to support the risk assessment, we need to feed different data sets into this. One of the first data sets we needed was the climate projections. This means the rainfall scenarios and soil moisture scenarios derived from the UKCP 18 data set, and also needs to feed the soil properties data and assets data into this risk analysis. So once we have got the models and data, we can then do a combined risk analysis, and finally we can use the DAFNI platform and also other our local computers to visualize the results as well. Now I'll introduce a little bit more about the data set we used. The first data we used is the rainfall scenario derived from the UKCP 18 dataset. So rather than just giving some numbers about the return periods, how they might change, we actually done this in a different way. So this work is done by our colleagues at the UK Center for Ecology and Hydrology. They have developed a widespread multi-day precipitation event. So basically, it's a collection of rainfall events that is spatially and temporally distributed to represent typical conditions in the current and the future climate. So this picture gives you illustration about what an event might look like. So basically, in the picture shows that in the north part of the England and also Britain, there's some rainfall events unfolding over there. So the data itself is represented by so we choose a typical event based on the probability of occurrence and also the spatial extent as well. So the current data has been made available for on both the DAFNI platform and another NERC managed data center as well. If you need more detail, you can contact our colleagues at UKCH. And to a little bit more about the methodology. So we want to really to get a very good statistical representation of the future extreme rainfall events. So apart from just using the raw data from UKCP 18, our colleagues at CEH, they have also developed a statistical approach to actually extend the event set so that it's a much larger event data set than just the raw UKCP 18 data set. So this data set has been really useful for us to understand the surface water flood risk to buried pipelines. Another data set we have used is the UKCP 18 soil moisture data. So again, it's derived from the UKCP 18 data set. What we did, again, this work is done by colleagues at CEH. So what we have done is that we run a national scale hydrological model to translate the climate data into soil moisture data at 1 kilometer square resolution. And then we run it using 12 ensembles, and then we use this to get the ensemble mean for the soil moisture, so that we can then basically get mean soil moisture every month from 1980 to 2080. Then we can later on overlay that with other data to get an understanding of climate risk to buried pipelines. We would also list the data about soil itself. It's basically about the type and the texture of the soil, because this would determine the mechanical properties of the soil itself, such as the Young's modulus. In other way, it's in simple terms, it's described how likely the soil is going to expand if the moisture increase, or whether the soil itself is soft or hard, how much load it can withstand. So then this data gives you us the information to infer those mechanical properties. So it's a 1 kilometer resolution data set. There is also final resolution data set as well. So we have got the rainfall, soil moisture, and soil type. And the final one we need is the asset data set. So basically, if we want to understand the risk to buried infrastructure, we list data for the infrastructure itself as well. In this work, we have done a case study about the natural gas networks. 2 networks are included. One is from the national gas, which is the open data set that was available online to the public. So we downloaded that, and the other one is the data from the Cadent Gas. Cadent Gas Network is the gas company managing the gas networks in the West Midlands region, and also part of the London and part of the northwest part of the east part of England as well. So it includes there are several data including pipe locations, diameter, and material, and we then overlay this data layers with other layers to do the risk assessment. So now I will give you a bit more detail about how the modeling actually is done for the for 2 different types of risk. The first one is the risk from surface water. As I mentioned, floods can cause both erosion and accumulation. So erosion can expose pipelines, but accumulation can increase pressure that is acting on the pipeline, so that it can cause damages as well. And we are using an open source hydrodynamic model to simulate the erosion and accumulation. The model is called Xilin Xia. It's been developed at the University of Birmingham, including several colleagues here as well. So this is what the model is. It's basically the hydrodynamic model solving the shallow water equations. It can simulate different types of hazards, such as floods and landslides and debris flow. It's open source, and it's also been made available on the DAFNI platform. as well. So we are just doing the final stage of doing the documentation, and then everyone can access it. But the code itself is open source. You can use it outside the platform at the moment. So basically, it's a model that has been well tested and runs on large computers, and it can also be coupled easily together with other models. So I won't give you a lot more. I won't spend a lot more time to explain this, but these are what the models gives us. It can simulate the flood and catchment scale, and also the geomorphology process, which we can use to calculate the soil erosion and the soil accumulation. In terms of the surface water risk part, we used a case study from the northeast of England. So we choose this region is because that it's a well-studied area known to have a high level of flood risk, mainly due to the relatively high amount of rainfall happening each year. And from our conversations with those utility companies, this region tends to have more problem. It seems to be a hotspot from their own understanding. So to support the modeling, we can use this elevation model, land type, and rainfall data to drive the flood simulations. So this gives you an example of what the simulation results actually look like. So from after running the model, we can get the spatial distribution of the soil erosion and the soil accumulation at catchment scale. So then building on top of this model, we have developed a framework to calculate the damage to the pipeline. So this work is being led by our research fellow Chen Li. So she has also joined the call today. And so to use the model outcome to actually calculate the damage to the pipelines, we have come up with a relatively straightforward methodology. Basically, we categorize the erosion and accumulation into 3 different categories. The first one is exceed limit. So basically, it has been fully exposed, or the accumulated depth of soil is large enough to cause large pressure. And then on the other end is the safe scenario, which means that even after soil erosion, there's enough depth so that the pipe is unlikely to be exposed, or the accumulation level is very shallow. It's unlikely to cause any problem. And there's another category, which is we call it possible to cause damage. Is the scenarios that it sits in between these two. And then combining the effect of both the erosion and accumulation, we can decide the overall risk level in 3 categories. One is low risk, medium risk, or high risk. Just example, if both erosion and accumulation give us the results of safe, is no risk. If any one of them, it's one of those more dangerous scenarios, it's high risk. If both are, if any of those sits in the middle, then it's the medium risk. It's a matrix based approach combining both the erosion and accumulation effects. So we have run the model for past events that happened at the end of 2015 and 2016. We called that Storm Desmond. It caused the major flooding problems for the region. So after running the simulation, we have seen that all the 4 pipes segments for the national gas pipeline running through the region has been categorized as high risk. As we can see from the highlight of this picture, is I think the critical points are the points where they cross the river. That's where a lot of river erosion has been happening. I think there's a kind of qualitatively confirmed what we have found from those companies' climate adaptation reports. It seemed to be that the river erosion is a big problem for them. So our modeling can qualitatively confirm this. So to actually quantify the climate risk, we have then feed the future rainfall scenarios into this models. So basically, for each of the period from the current period from 2020 to 2040 or the future period 2060 to 2080, we randomly choose some events, but we from those more extreme events, from the less extreme events, in each of the envelope, we choose randomly choose some events. So for each of them, we basically choose 12 events for each of the time period, and then we can then feed that into the simulations. So again, for the national gas pipeline running through the northeast of England, we can see that comparing today and the future, in the future, there will be more events that can cause problem. So this confirms that from our modeling, there is indeed an increase of the risk from surface flood-driven surface erosion. So that's what our results has conformed. And the other part of the work we have done is actually to try to model the damage of groundwater movement of seasonal changes of soil moisture. So this work was led by another research fellow called Niklas Rappas. He's now at University of Warwick. Hopefully he's also here today. Later, he can also answer your questions. What we did is that we developed a finite element model to simulate the soil pipe interaction. The soil moisture are being used to estimate the soil stiffness and expansion shrinkage volume. This simple model has been validated by a more complicated three-dimensional finite element model being developed here at the university's National Barrier Infrastructure facility. So we simplify the pipe into basically we simplify the pipe into a line so that we can run the model for the entire network. So that's why we conceptualize it in this way and develop the model. There are some key assumptions for the finite elements modeling. It's solving a 2D Eulerian beam equation using finite elements methods, and the swining and shrinkage from the soil due to moisture change is being applied as external loading to the pipes. So the same model is applied to each individual pipe section. So basically, we are not running the model continuously for the whole network, but basically for each of the pipe section of the data, we apply this model once. So which means that for an entire network, maybe we need to run the model maybe several thousand of times. So that this is how we do that. And to consider the variability of the soil, basically we divide that into active and passive zone. For the passive zone, we use a reference, so it's moisture value derived from the average mean, and the active value is actually the actual value we got from our data set, so that we use this assumption to capture the variability, the spatial variability of soil moisture. So once we have calculated the movement of the pipe using this finite element method, we can then categorize the risk coding by comparing the simulated displacement with the failure displacement. So as a comparison, alongside developing this finite element model, we have also developed a simple risk matrix-based approach to basically just put all the possible factors into a matrix to qualitatively quantify the risk level. Then we have got some results for this part of work as well. So we can then see the comparison between the finite element model and the risk matrix-based model. Basically, the finite element model gave a lot more granularity in terms of the results. So that's why we choose to use the finite element model. And then we have basically run the models for each of the months from 2080 to from 1980 to 2080, and we have done some comparison for the same months of the year between 2020 and 2080. As we can see that we could see more yellow colors and red colors, which means that the risk level is increasing. And this probably gives you a better idea of how the risk is changing. We summarized the total amount of high-risk pipe sections and plotted for the whole 100 years to see how it's changing. So I mean, don't take this result as it is, but I think it's qualitatively give you the trends and the hotspots we have identified. For example, the North London, East Anglia, it's somehow comparable with the information we got from cadent gas. And the seasonal trend is more interesting. We can, from a soil moisture change perspective, clearly we have seen trend for increasing trend for summer, but from the winter, it doesn't really change as much. And we have also done some sensitivity analysis. We basically look at how the soil moisture correlates of the risk level. During the winter, basically what we can see is that the higher soil moisture is causing problem. But during the summer, we can also see that lower soil moisture is also causing problem. This is because whenever you got high soil moisture, it expands, it causes problem. But you also have the problem when soil moisture is low because it shrinks, it also causes problem as well. And not only soil moisture, the pipe itself, the diameter is is related to the damage as well. Basically, if the diameter is smaller, and we have seen more problems. This is because smaller pipes tends to be more vulnerable to those movements. Finally, I want to give you some introduction about the DAFNI platform. And we basically developed our model with the support of the DAFNI platform, and we implemented our model on the platform as well. So it's 8 million investment from EPSSC and as part of the UCRATE program, now managed by FC, and so basically it has got investment from UKI to develop such a platform to allow users to share data, develop models, and also to visualize the results as well. So this is how the visualization looks like on the platform. And now I will invite my colleague Chen, who is also on the call, to share her screen so that she will be able to give you a very quick demonstration about how the visualization is actually looking like on the screen.
Hi, everyone. I'm Chen Li, and I'm a research fellow at the University of Birmingham and working on STORMS project. I would like to show you how we do the visualization of this project result. And I would like to share my screen first. Yeah. Can you see my screen?
Yes, we can.
Yeah, thank you. And so for the STORM project, we do lots of simulation and we can have our result. Our result, one of the STORM format is a shapefile. So you see this just a part of our result is in the shapefile format. We can visualize it in any GIS tool, but we also have developed code to visualize them in the DAFNI platform or in any other HPC server environment. And here I would like, because of the time limit, I won't, run the code one by one to the visualization, but I would like to show you some part of the result. I've saved it before, and let's have a look. So this, like Xilin introduced in STORM project, we access the underground pipe by two methods. One is FEM model, and another one is the surface floods rainfall model. So this is the result from the FEM model. For the FEM part, we run the simulation from 1980 to 2080, 100 years. And this is a result from the 2020, the first months of the 2020. And we can see the...
I think I can only see the folder. Did you share your full?
Yeah, sorry, we can only see the folder.
Yeah,
Sorry.
maybe you could just share your full screen instead of the folder.
Yes. How about this time?
Yeah,
Good,
that's
good.
great.
Yeah.
Thank you.
Yeah, that's better. And so this is the result from the 2020, the first month of January of 2020. And it's the simulation of the national gas network and the cadent gas work. And we can see lots of lines here. These lines represent the underground pipes, and they have a different color. Like this, the legend bar, the green color indicates the pipe is under the low risk. Yellow color represent the medium risk, and red color indicate the high risk. So from here, we can see the risk distribution. And when we zoom in, yeah, because the data is quite large, and we can see some detailed properties of the pipe. Let me have a look.
Yeah.
Yeah, it's a little bit tricky to capture. Yes, so like if we just zoom in to have a detailed look, we can see, okay, the pipe location, the pipe, the soil properties like the soil depth and type, and also the pipe diameter, pipe attributes. Lots of the information here we can have a look, and also we can compare the results from the different period. So like this is the result from the 2055. And I also I have also produced a result from the 2080. So from the different time period, we can also investigate how the climate change impact the underground pipes and to see the distribution change of the underground pipes. And this is from the FEM model. And like Xilin introduced, we have also used another kind of the method to access the underground pipe, which is the surface floods. And we choose the Eden as the simulation area. The Eden catchment is quite large in the northwest of the England. And we have simulated a real historical event, Desmond storm. It happened in the 2016, and for this storm, it caused severe floods. So the severe floods may have also caused the surface soil movement, like the accumulation and erosion. And from the results, we can see that all of the pipe in this catchment suffer the high risk because they are red. And we also identify the locations where the high risk happened, like where the high accumulation happened and the deep erosion happened. And if we zoom in to have a look. So for this area is in the river, and we see this location is the blue, which means the high risk location of the accumulation. So for this, the accumulation value is around 1.5 meter. So this may cause extra pressure for the underground pipe at this location. And we can also see some purple points here. It's the deep erosion points. And so we can see the erosion value is around 1 meter, which means for this event, the Desmond storm may cause the 1 meter erosion here at this location, which may cause the pipe to be exposed. So this is the event, the real event. And we also consider the climate change in the future for the floods, for the surface soil movement in this catchment. And we have simulated different events in the future and consider the different rainfall intensity. And like this event, it happened between the 2060 to 2080. And it is a very extreme event. So you see, it caused the high risk for this catchment. And we have also simulated some event, the future event with the moderate rainfall intensity. And for the moderate rainfall intensity, the high risk level is more about the medium and low in the Eden catchment. And this is the event, the future event with a mild rainfall intensity. And under this mild rainfall intensity, we can see all the pipes in Eden catchment are safe. So we have, of course, we have simulated lots of multiple events, future scenarios, but here we just demonstrate 3 as an example. And we have upload, the results in the DAFNI platform, and we can also share the program we have developed for the visualization. If you are interested, you can contact us directly, and we can show you the program and the result for the further analysis. Thank you.
Yeah, thank you, Chen, for this excellent visualization demo. And what I will do now is to quickly wrap up this presentation with some summary. So basically, the main outcomes from the project is that we have developed a framework for quantifying climate risk with the associated models and data sets. I think all of them are on the platform, and we are just finalizing the details, tidying up, and so that we will be able to release it to other users fairly soon. And then we have done some initial risk assessment for the gas networks so that it demonstrates the capability of the model, and also gained some new understanding of how we might work with those utility owners with other different organizations as well, so that we can better integrate our data. And potentially, I think that this work could potentially help risk assessment and also awareness at the national level, and potentially could provide evidence for some ongoing work about national level climate risk assessment, and also testing different scenarios of adaptation as well. The challenges we had was that, of course, there's a lot of uncertainty for the modeling and risk assessment. And part of the reason is due to some data being unavailable or non-existent. For example, the buried depth of some of the pipelines, they are not always available or even existent. For the next stage, it could be addressed by linking with other initiatives, such as NEWA National Underground Asset Register and Jasmine data form, which is data form for sharing climate data and other environmental data. And we would also be very keen on seeing people from the industry or from other academic organizations to use the model and to collaborate with us, and so that we can look at other problems such as interdependencies. And we also have got some ideas to further improving the methodology. So I hope this is interesting, and thank you for all your attention.
Thanks very much, Xilin, and Jian, great that you could join us today. Thank you for that demo. That was really illuminating. I'm going to open it up now to questions. We already have questions in the chat, so I'll just start there. So thanks, Xilin, for the presentation. I have a question about the data integration process. When analysing the effect of precipitation on infrastructure, some damage may not be immediate, e.g. within a single day, but could possibly result from cumulative effects over time. Does your model account for variable temporal ranges, or does it use a fixed time frame when integrating weather and infrastructure data?
So yeah, that's really a great question, and it's something that we actually have been thinking about. So currently, the methodology for surface water part, it's event-based. For the ground movement part, it considers soil moisture variability on a monthly basis. So they are fixed temporal window, but we are aware of the cumulative effects of those things such as ground movement, which it can weaken the soil by just accumulating whitening and drying cycles. I think this is the next step we would like to consider.
Thank you. Do we have any other questions, please? Those are all those in the chat. Everyone's feeling very shy today. I think you did such a detailed presentation. I think you've probably answered everyone's questions.
I hope so. Thank you.
Okay. Okay, no takers? Oh, nope, another one. Oh, just everyone saying great session. Thank you on the chat. Okay, well, I think that concludes today's webinar. Thank you so much to Dr. Xia and Lee for joining us today for a fantastic presentation. The recording will be available and for anyone who couldn't make it today, so please let your colleagues know. And yeah, we look forward to seeing you on our next webinar, which will be presented by our director, Brian, on the 21st of May on the DAFNI project. Thanks very much for joining us today, and hope you have a great rest of the day. Thanks very much. Take care.
Yeah, bye-bye.